Okay, let's take a look at lattice energy. That's that ionic compound stability strength measurement. I think of it as that energy that holds that lattice together. Well, I guess that's pretty basic since that's the term right there. We could also think of it as the energy required to completely separate 1 mole of a solid ionic compound into gaseous ions. Now, for that, I assume we would have an energy unit that would be joules per mole. I'm sure you could also come up with an energy unit that would be joules per bond. In any event, here's the formula for it. That energy, E sub L, that lattice energy, is equal to some constant, which is going to vary from substance to substance, something that you probably look up, times the charges that each ion has, the positive one and the negative, divided by the radius. That's the distance between them. So right now you should be able to figure out a qualitative understanding of what it's all about. And it's about what you'd expect. It's not like this is rocket science. It's if the charges are really high, like +3 and -3, well, that's going to give you a stronger attractive force, and that'll give you a stronger energy. If they're super close together, meaning that that is a low value, then that would make this overall higher also. If they're far apart, it becomes weaker. So just use common sense. Strong charges and short distances make for high lattice energy. And you could go ahead and calculate it. AP emphasizes the qualitative understanding of this. I think it's relatively rare that you'd have to calculate this out. They're the definition terms that we just said. So we could try to take a couple substances and figure out what's the deal, which is going to have a stronger lattice energy. Well, the only difference here is the magnesium to the fluoride bond versus the magnesium to the oxygen bond. So magnesium's common to both of these, but the magnesium oxygen ion is a +2 -2 system. These are +2 -1 systems. So you're going to have a higher value on top, and therefore the lattice energy will be stronger, predictably, for magnesium oxide. And there's the reason. Now here, it's just +1 and -1, so we can't use Q values as a indicator, but we could use electronegativities. I mean, lithium fluorine has a greater difference in charge, a little bit more plus, a little bit more minus. It's almost analogous to dealing with polar covalent bonds and trying to see the differences. So I would predict this to be a stronger bond based on the differences in electronegativity values. Everything else is probably going to be about the same, and so there it is, smaller bond. The radius will be shorter. That's not what I said, but that makes sense. If the attractive forces are stronger, the radius will be smaller. They'll squeeze closer together. And here's a bunch of them. You can try to understand each one of these, and you should be able to do it by using these two basic facts. Lattice energy increases as the charge, that's Q, increases, or the radius decreases. And that's pretty much it for lattice energy. One little thing to be aware of, and this drove me crazy when I discovered it, is that you might see another formula in a textbook for this, and it's defining lattice energy not in terms of energy, but in terms of force. Force and energy are not the same thing. Physics people will probably laugh at me, but that's about where I would stop there, and I would just say, fine, watch out for the force version, watch out for the energy version. You'll see that the force version varies with r squared. That's for physics people, in my opinion, not so much for us. Just watch out if they're asking for force, use that formula. If they're asking for energy, use the other formula. And that is lattice energy.